Okay, so what I'm going to do is I'm going to talk about limits, and I'll stop the recording and start it again for any other requests that you might have. But I thought, since someone asked about limits, and also since it's a bit bright, isn't it? Don't know how to fix that though. That's no good at all. Damn. Alright, just leave it at that. Also, there isn't one already there on limits, so it couldn't hurt to have one there for future students. Okay. So, the reason why limits are in this course is because they are there so that you can talk about continuity and differentiability. That's the purpose of them. And also, just because most things are about limits. And also so that you can do things like improper integrals and various other things that involve infinity as well, involve limits too. So that's why they're there, and it's always a good question to ask why a topic is in your course, and sometimes it's just so that other courses, other topics can work. Okay, I'm not really going to go through the theory of it, but what I am going to do is just talk through some of the deal with how to cope when you're asked to find a limit, and that will do enough to deal with how limits work. So there are a couple of things that it is worth mentioning before we even start about the basic, most common limits. So step one, our common limits that you're just supposed to know the answer to. That's really bad, isn't it? Is it going to adjust its... go in a bit. That might work better. Okay, so common limits you're just supposed to know the answer to. The limit as x goes to 0 of 1 over x does not exist. That's one of the ones you're supposed to know. And the limit as x goes to infinity of 1 over x is 0. They're ones that you're just supposed to know off the top of your head. In fact, this one is true if anything on the bottom is like x squared or x cubed or e to the x, they'll all go to 0 if it's on the bottom, and you're allowed to just say that. Those two things in particular are really useful to know, x squared and x cubed, and both of them are equal to 0, okay? But I might just move this over a bit and just put them both in. Okay. Just because it's just good, they're really part of this thing here, they come from that, but you're allowed to just say that if you want. Okay, that's the common limits involving x's, and then the other really common limit you want to know is the fundamental trig limit. The limit of sine x over x is 1. You are allowed to just say that it is 1. It's very rare that you're asked to prove it, and that is what it is. This is called the fundamental trig limit. And the reason it's fundamental is it's actually quite difficult to prove, and you have to make reference to triangles and circles and stuff. And it is the limit from which all the derivatives of trig functions come. Okay? So trig functions, their derivatives and their limits their derivatives all come from the limit of sine x over x as x goes to 0. And that's why it's fundamental, because all the other ones are based on that. So there are common basic limits, and that's pretty much the deal. And then there are these laws of how to deal with limits. And I don't know how they're numbered, and it's probably not good to number them. So if you ever want to use a limit law and explicitly say which one you're using, you probably can just say because of a limit law and not specify which one, or say the limit law for something, which is how I think about them. Okay, so there's the limit law for addition. So the limit as x goes to anywhere of some function plus some other function, you can separate your limits out over addition. Limits expand out over plus. Okay? Unless one of these limits doesn't exist, and then you're not allowed to do it. Okay? You're only allowed to expand out and use the limit laws if all of the limits involved individually exist. Okay? So all individual limits must exist. I'll do some examples in a second to just ram that home, but that's the basic idea. Okay, so if these individual limits didn't exist, I wouldn't be allowed to expand it out, but I might still possibly be able to calculate the limit anyway. And that works just as well for subtraction. Okay, so the limit sign can expand out over addition and subtraction. There's also a scalar multiple rule. Which says that the limit as x goes to anywhere of constant times f of x is constant times the limit as x goes to anywhere of f of x. So you can bring constant out of the limit sign. So in that way it behaves the same as derivatives and it behaves the same as integrals, and in fact that's why you're allowed to do that with derivatives, because limits behave that way. Okay, so in your notes, that's called limit law number 1, both of those together at the same time. Okay, limit law number 3, which is just for ordinary multiplication, or 2, or whichever number it is. The limit law for multiplication says that if both of the limits actually exist, you can expand limits out over multiplication as well. Okay? Remember, there is a caveat that this only works if both of these limits exist. Okay? If either one of them or both of them don't exist, then you are not allowed to expand out over multiplication. It may still be possible to figure out what the limit is, but by some other method. There's a limit law for division as well, so we've covered addition and subtraction, scalar multiplication, proper multiplication, and there's a limit law for division too. And the limit law for division is the only one that will tell me if a limit doesn't exist. Okay, so the other ones so far will tell me if some limits exist, then another one definitely does exist. But it doesn't tell you anything about when limits don't exist. But the limit law for division is the only one that tells you when a limit doesn't exist, which is a clue. If your lecturer asks in an exam question, calculate this limit, or say whether it doesn't exist, it is almost sure that you will use some argument involving the limit law for division. Okay? So the limit law for division says this. we want to calculate the limit as x goes to 0 of some function of x over some other function of x. That's what we're aiming to achieve here. And there are three situations. There is the situation where the bottom is 0. There is a situation where the bottom isn't 0. And there is a situation where they're both 0. So there's three. So if the limit as x approaches a of g of x is 0, and the limit as x approaches a of f of x isn't 0, so the bottom is 0 but the top is, then it doesn't exist. Okay, top isn't 0 but bottom is, the limit doesn't exist. If the limit of the bottom of g of x isn't 0 and the top exists, then you can expand it out over the, you can do the limit of the top and bottom separately.
Does it have to be as x goes to a or what x goes to?
Oh yeah, a. Lucky that a looks like 0 can be turned into an a really easily. Okay, note this includes the situation where the limit of the top is 0. Okay, so if the limit of the bottom isn't 0, just do the limit separately and it'll be fine even if the top is 0, you know. And limit of f of x is anything including 0, then you can just expand the limit into the to the division. Okay, so we've got the limit of the top is 0, the limit of the bottom is 0, and the limit of the top isn't. That's the first thing you should check. The limit of the bottom isn't 0, and the limit of the top is, well, anything including 0. That's fine. And then the last law, but basically this is the totality of the law, of this limit law. The problem with it is it doesn't actually tell you what happens if they're both 0. So oops. Okay, so if they're both 0, then this limit law gives me no information and I have to use some other method to figure out what's going on. And in fact, if either of the limits doesn't exist, it also tells me no information. Classic. Okay. So if they're both 0, there are a few things you can do, and I'm going to cover them in just a second. But in fact, I might do it now, because when you're studying for things, you should do them in a different order to the way they're done in the lectures so that they work better in your brain. So let's just see where we've been. Addition and subtraction, you can expand your limits out over it as long as both the limits exist. Scalar multiplication, you can bring the scalar out as long as the limit exists in the one that's out exists. Multiplication, you can bring the limits inside as long as both limits exist. Division, if the bottom is 0 and the top doesn't exist. If the bottom's not 0, then just do it. You just expand it out. And if they're both 0, what do you do now? And that's what I'm just going to talk about now before I move on to the very last limit law. So if they are both 0, yep.
What if f of x is d on that last one?
If any of them don't exist, then it tells you nothing at any point, and that goes for all these limit laws. Okay, with these limit laws, if any of the limits don't exist at any point, you're just stuffed. Okay, you've got to do something to the limit before you can figure out what to do.
So the limit may or may not actually exist. It's just that didn't help you find it.
That's right. So the comment for those who are listening on the video is that if one of the limits doesn't exist, then the big limit may or may not exist. It's just that this rule doesn't help me find it. Okay, so if the top and bottom are both 0, what if the top and bottom are both 0? That's our question. And you'll find in almost all exams if that will happen at least once. Okay? Otherwise, there's nothing fun to do to prove that you know how limits work. Okay, so if the top and bottom are both 0, you've got a couple of options. One is to factorise the top and the bottom and cancel out the part that's 0. Okay, so this isn't really a rule, but if they're both polynomials, you know, x squareds and x cubes and stuff, it must be possible to factorise them to get x minus a, because when you sub in a, they come out to 0, which is how you tell that there's an x minus a. Okay? So it must be possible to factorise both and cancel an x minus a. Okay? It must be possible to do that. And in fact, they will usually set it up so that you can easily tell that. And that's a clue, right? If the limit as x goes to 4, as the top is 0, it must be possible to factorise it with an x minus 4. So your normal things where you're going, how do I think of two factors that multiply to give that one? Well, you know one of them already. So it makes it a little easier to factorise. I'll do an example of this now.
Are we likely to be asked to factorise a cubic?
I don't know. Usually factorising cubics falls down to situations where it doesn't have a constant term, so you can pull an x out. And that means that it's just x, something else. And also, it would be a very nasty person who would expect you to do this, but since you know what one of the zeros is, you can do polynomial division to factorise it.
Yeah.
It is evil, but certainly not impossible, but unlikely. I mean, your lecturers this semester are very nice people, and so it should be, I would not expect that, but possible. Give me a second. Let's do that one. Yay. So I've given you the classic cubic that they might give you, which that's all good x's. Okay, this is a classic example, and to do your working with full rigour and good writing, you're supposed to separately calculate the two limits, but I would say the limit as x approaches 3 of x squared plus minus 7x. You don't have to write this step down, but it's useful. Would be 3 squared minus 7 times 3 plus 12. I'm really hoping this is going to work out. 7 times 3 is 21. 3 squared is 9. 9 plus 12 is 21. So that will come out to 0. the limit as x approaches 3 of the denominator (3 cubed minus 6 times 3 squared plus 9 times 3), or 9 times 3 is 27, so is 3 squared. So we've got two lots of 27. 6 times 3, 6 times 9 would be 54, which is 2 times 20. Okay, so it comes out to 0, which is what the whole point of this example was. So that means it's possible to factorise. So therefore my limit as x approaches 3 if I was being really clear-minded, I would factorise them separately outside the limits, but I didn't think to do that. And I'm not going to rub it out. So we know that x minus 3 factorises into this. So we know that minus 3, that 3 and something multiply to give 12, so the other one must be 4. Okay, so x minus 3 and x minus something expands out to give this, and the two somethings multiply to give 12, so the other one must be 4. I don't even have to check the addition, it does work. Minus 3 plus minus 4 is minus 7, so great. On the bottom, I can factorise an x out, right? Because it's x cubed, x squared, and x, so I can pull the x out. And that's going to leave me with x squared minus 6x plus 9. Right. Now I know that that's actually x minus 3 all squared because I happen to be able to factorise squares. But you can do the same trick. You know it must have an x minus 3 as a factor, and these two numbers have to multiply to give 9, so this one must be a 3 as well.
So you can just do that when there's no constant term, you just pull an x out?
Yep. If there's no constant term, pull an x out. Yep. So cancel out the x minus 3's. You're allowed to do that because technically x actually isn't equal to 3, and therefore x minus 3 is not actually equal to 0 because I'm only doing the limit. It's just close to 0, so I can still cancel it out. And now the limit of the top. So now we've got the limit as x goes to 3 of the top is minus 1, and the limit as x goes to 3 of the bottom is 0, so therefore my limit doesn't exist because the top is not 0, the bottom is 0 and the top isn't. So therefore the limit as x approaches 3 of whatever the original thing was does not exist. If the bottom hadn't come out to 0, then I would have just subbed it in and it would have been fine. Okay? So, I mean, you can probably skip that step if you want to, if you're in your exam. If you just quickly do it in your head and go, or on the calculator and go, all right, they're both 0, I'm going to factorise. Okay? You don't have to write that bit on the page, but you do have to write this bit on the page, because that's the reason why this doesn't exist. Okay? And that would be the limit law for division. Okay? That's the reason why. Yes?
Would we have to write that as the original limits exist to use the division law, like at the very start?
Yeah, that's probably true. In fact, this is, to be able to use... no, it doesn't matter, because this limit, whether it exists or not, is the same as this limit. So they either both exist or both don't exist. It's these ones that exist which is the key.
Yeah.
Cool. Couldn't hurt, though, to say they exist and are equal to 0. It never hurts to write down working, though. It's almost never a bad plan. Okay, so what else can you do? Okay, that's plan number one. What else can you do? Well, you can do L'Hopital's rule. Actually, before that, what else you can do is look for the fundamental trig limit. Okay, that is the other thing you can do. And it's best to do this by example. Just try and think of one. Might even be one in your notes. No, I'll do a new one. Okay. The limit of tan x over x. This is a classic. The limit of the top is 0. The limit of the bottom is 0. So we're in a 0 over 0 sort of situation. So we're going to have to do something other than subbing in. Okay? So what we're going to do is, because it involves something trig-ish, we're going to look for the fundamental trig limit. Which means we're going to have to put a sign in here somewhere. So I can do, the tan can be replaced with a sin x over cos x, which would introduce a sign. We need a sign because we want to use the fundamental trig limit. So, whoa, yeah. Dropped my microphone. I'm going to go sin x, going to rearrange that fraction. There are two ways to deal with it. One is to multiply the top and the bottom by cos x, and the other one is just to know how fractions work. Sin x over cos x times 1 over x, that's the other way of doing it as well. Dividing by x is the same as that. And so I get sin x over x times 1 over cos x. Now here we go. Sin x over x, when x is 0, that limit is 1. Cos x, when x is 0, is 1. So the bottom's not 0 when I do this one, so I can just separate my limits by limit law for multiplication. You probably don't have to give a reason why you're allowed to do that, but that's the limit law for multiplication. And this limit is 1, and this limit is 1 over 1, so the answer is 1. So that's your classic trick number 2 for when there's 0 over 0. And the final trick is L'Hopital's rule. Just a note about French spelling. If an English word, if your French word looks very much like an English word, but it has a missing S, there's a circumflex accent on the O. There you go. Of course, people actually who live in France can't spell, so probably doesn't make any difference. Yes.
Because it's the same.
It's the same word. Of course, hospital is actually an Arabic word, but we'll move on from there. Okay. So L'Hopital's rule is specifically designed for the situation when both the top and the bottom are 0. That is the only time you're allowed to use it. That's what it's for. And it goes like this. So you have a function f of x over g of x. Okay.
Is that the only time?
Oh, well, technically the top and bottom can be infinity.
Or minus infinity.
Yeah.
There was a question in the past exam I saw that tripped me up because I didn't realise you could use it.
Yes. So, but I'm looking at the moment at the what happens if the top and bottom are both 0. I'll deal with the other one in a different spot. Okay, so if they're both 0, so if the limit of f of x as x goes to somewhere is 0, and the limit of x goes to somewhere of g of x is 0, and they're both differentiable, at the point A, that's the key point, then, so this is what we're interested in, that function, then the limit as x approaches A of f of x over g of x is the same as the limit as x approaches A of f dashed of x over g dashed of x. Okay, it is extremely important to point out that those two things are not equal. F of x over g of x is totally not and almost never f dashed x over g dashed x. The point is that even though they're different functions, we will have completely different graphs, they will have the same limit as x goes to A. So the point is that that graph and this graph at the point x equals A cross. Okay? So I just want to point out that you are not allowed to write that statement because it's not true. You can only write it if the limits are there. So, yes, you will lose a mark as well, But just, from the fundamental truth of mathematics, it's just not true, so don't write it. Okay, so that's L'Hopital's rule. And there is a technicality, you're not allowed to use it to do sine x over x. Because the only way that you know how to differentiate sine x is to know the limit of sine x over x as x goes to 0, so it's all circular reasoning. So, everything else is okay. But the fundamental trig limit, you're just supposed to know what it is. You don't use L'Hopital's rule. L'Hopital's rule will remind you what the answer is, but you're not allowed to prove it using L'Hopital's rule. That's circular reasoning. So just as an example, that limit. So the limit of the top is 0. Actually, totally not. Right. The limit of the top is now 0. The limit of the bottom is 0. Actually, I'm just going to change that to just an x because I want this one to exist this time. The limit of the top is 0, the limit of the bottom is 0. So if I differentiate the top and bottom, derivative of e to the x is e to the x, derivative of 1 is 0, derivative of x is 1. So this is using L'Hopital's rule. And now I can just sub it in because the bottom's not 0 anymore. Yay! Note that if I had the x squared, my new limit would have been not 0 on the top and 0 on the bottom, and it wouldn't have existed. Okay, so L'Hopital's rule also tells you when things don't exist. Either they're equal, or I can put sort of in brackets, or both don't exist, right? So if this one doesn't exist, then neither does that one. Yep?
In the example, would it be direct in which technique to use?
No.
So could you use L'Hopital's rule?
So back here, if you were doing the polynomial, right? This one, you could have used L'Hopital's on that too, if you wanted. Or it is possible in the exam that they will say, find this limit without using L'Hopital's, right? If they don't say, then you're allowed to use it. What was that? You weren't allowed to? Yeah. Yes?
Is there any reason not to try and use it first and say try factorization? Will there be questions that won't work out using it or not?
No. If polynomials are differentiable, L'Hopital's rule will work.
Yes, we do.
So I point out the polynomial one because sometimes they do say not allowed to use L'Hopital.
Yeah.
So, and plus, sometimes it's so obvious with the polynomial that it's not worth differentiating it. You know, it'll be like x squared plus minus, there will often be like x squared minus 1 over x minus 1, and you go, okay, I can factorise the top, is x plus 1. Yeah. But, you know, in an exam, whatever occurs to you that is not contrary to your instructions is the thing you should do. Okay, if you have multiple things, then choose the quickest one, but if only one thing occurs to you, then do that. And if it's like, sorry?
If x squared is on the bottom,
yep.
is it applied the rule again?
No, it wouldn't have worked. You can do the rule multiple times, but in this case it wouldn't have worked if I did it again. I'll just do that example. So now the limit of the top is 1 and the limit of the bottom is 0, so it doesn't exist. But if the limit of the top and the limit of the bottom were still both 0, I'd do it again. So you can do L'Hopital's as many times as you like, as long as at every stage it's 0 over 0. But that does not exist by my limit law for division. Because the top is 1 and the bottom is 0. Okay. Right, I'm just going to do some examples. Just before I finish, I'm just going to add the limit law. The limit laws for infinity are the same. You just have to know basically this. That is the key thing about limits at infinity. Oh no, there is one more rule. There is one more rule. But before I move on to that, I just want to do an example. There are two more rules, but I just want to do an example that doesn't use any of them. Give me a second. That. Pretty sure this will work. One more second. Oh, crap. Right. Okay. Right. So, you would expect with a multiplication that you would do the two limits separately. But, for a start, that's 0 over 0, so I have no idea if it exists. And this one totally doesn't exist because 1 over 0 doesn't exist. Okay, so I can't do the two limits separately because my limit laws prevent me from doing that because one of the limits doesn't exist. So therefore, I have to do some algebra first so that I can turn it into something else. And the only, the limit law for division is really useful, so I might as well convert everything into a fraction. So I just times the top and bottom of my 1 by x, and then I had a common denominator. So that's what I did for that. Now let's just check, are we any better? No, this one still doesn't exist. The top is -1, the bottom is 0, so that one still doesn't exist, so I'm going to have to do even more work. I should try and multiply my two tops and bottoms together. Okay, so now the top is 0 and the bottom is 0. So at this stage, if I wanted to, I could use L'Hopital's rule. Okay, if I was of that bent. But because these are only really easy to factorise, I'm going to just try factorising, because I know that if they're polynomials, which they currently are, I'm going to get this. And then this x squared cancels with those two x's, and this x minus 1 cancels with those x minus 1's. And now it's just x plus 1. And I can sub it in. Yay! I should have gotten one. My answers have all been 1 so far. Please don't take that as the general answer. Beware of the toast. Okay. Cool. I'm just going to do an example of doing an infinite limit. You do that one. So we can go to infinity. So what that's asking us is that this graph might do all these weird wiggly bits in the middle, but then it'll sort of flatten out at the ends, and we're saying, well, what function, does it flatten off and level off to a straight line, a flat line? That's what I'm asking. Okay, so just for intuition's purposes, if the biggest power on the top is smaller than the biggest power on the bottom, the limit will be 0. So this limit is going to be 0. That's not good enough in to show working, but that's your intuition. If the biggest power on the top is more than the biggest power on the bottom, the limit doesn't exist. And if they're the same, the limit will come out to a number. So I know this limit's going to be 0. Okay, first up. But the key is that the only limit that we really know at infinity is that one. Possibly its friends, 1 over x squared and 1 over x cubed and all of those. Okay, so I should convert this to include the only infinite limit I really know. So what I'm going to do is I'm going to divide the top and the bottom of my fraction by the biggest power I see anywhere in the whole fraction. Okay, the biggest power I see anywhere in the whole fraction is x to the 5. I'm going to divide them both by x to the 5. So x cubed divided by x to the 5 is 1 over x squared. 2x divided by x to the 5 is 2 on x to the 4. 1 divided by x to the 5 is that. X to the 5 divided by x to the 5 is 1. X squared divided by x to the 5 is x cubed. So now I get this. I'm allowed to do that because x is not infinity, it's a number, and being a large number, it's not 0, so I can divide by it. And now, the limit of the top is 0 and the limit of the bottom is 1. So since the limit of the bottom isn't 0, I can just sub it in. Okay, each of those pieces on the top, the limit is 0. The limit of the bit with the x in it on the bottom is 0. So I get 0 over 1, which is 0. Of course, L'Hopital's rule would have worked too. L'Hopital's rule also works if the top and bottom are infinite when x is infinity. But this is quicker. So, at least in my head. Alright, so I do have a couple more limit laws to go. Okay, so far, just to make sure we've got a handle on what's going on here. So far, we've had a limit law for addition and subtraction, a limit law for scalar multiplication, a limit law for multiplication, a limit law for division, which has been the most useful limit law so far. And then we've had a couple of tricks to use when you've got 0 over 0 in your limit law for division. We've got our factorise and cancel, we've got our look for the trig limit, and we've got L'Hopital's rule. So those are all things to use when I get a 0 over 0. Okay? Cool. So, there are two more laws. One of them's a theorem. So, the limit law for substitution. In your lecture notes, this is called limit law number 4. And it's really hard to write it down mathematically so that it makes sense. Okay? Basically, it says that you can bring limits inside functions. Okay, so that's one way of saying it. So as long as your function is continuous at the point where the limit goes, you can bring it inside. So this is version 1. Okay, so version 1 says that the limit as x approaches a of f of g of x is the limit as x approaches is f of the limit as x approaches a of g of x. As long as f, the limit of f at whatever this limit is exists. Okay? But basically, as long as f is continuous, it'll be fine. At the relevant point. Okay? But this will be fine. So if you go like the as an example, the limit as x goes to 0 of e to the x squared, no, that's not useful. It's just obvious, okay? No, like, I'm just trying to think of an example where it's not really, really obvious that you could just sub it in. Like, in the end, you're just subbing it in. You're saying, well, if you can sub it in the inside, you can sub it in the outside. But there's this, limit of ln of, x squared plus 1 over x minus 1 or something. Just as a crazy thing. Really hope that exists. No, just a second. Right. Still doesn't exist. Right. Okay, so the limit as x goes to 0 of that, you can, because ln is continuous, at least at most places, and it'll be okay as long as I can do this, we can just bring the limit inside. And since that's not 0 on either the top or the bottom, it'll just be the limit ln of 1 over 1, which is 0. Okay, so that's the basic substitution law. It's really the bring inside the function law. But it's even better than that. Okay, so the limit law for substitution, limit law number 4 in your notes, is even better than just bringing limits inside. Because really, there's no particular reason why I had to do this bit of working, because surely I could just have subbed it in, right? And you go, well, that's, I can sub that in. There's nothing wrong with that at all. So I could have just subbed it straight in and nothing would have been a problem. There's no particular reason why I have to write this line of working at all. But version 2 is awesome. Okay? Version 2, it may be that the function inside only exists as a limit. Okay? So, right? In fact, I should have been really, really clever, and if I put sine x over x here, okay, I would have had to bring the limit in. So if I had changed this to this, then it's great. I need to use this limit law for this. Awesome. Okay? Because sine x over x doesn't exist when x is 0. So if I bring the limit inside, the limit does though. Okay? So that'll work really nicely. I can't do this by just subbing x in, but if I do bring the limit, then that limit comes out as 1 and I'm good. Version 2 is designed for situations when the outside function is the one that's the problem. Okay? This one, the inside function, was the one with the problem. I had to do a limit there. What if it was sine x over x? That was my outside function and I had something else inside that. That's when it's really cool. Okay? And it goes like this. It goes, see if I can say this right. It's easier to do not as limits but just as goes to symbols. If g of x goes to, say, b as x goes to a, so the limit of g of x is b as x goes to a, crap. Ignore that. Try again. Okay, so let's see. So we want the limit as x goes to a of f of g of x. Right? Cool. What we're going to do is we're going to say let u equals g of x. So it's substitution. This is the deal. Just like substitution for integrals. Let u be g of x, and then we'll say as x goes to a, then that means that u will go to somewhere. Whoop. So no, leave the as. If as x goes to a, u goes to b, then the limit as x goes to a of f of g of x is the limit. And here we go. The g of x is replaced with a u. The x goes to a is replaced with the u goes to b. That's the limit law for substitution. Okay? So you want something, and this is useful for when the outside function needs a limit. You know, when the outside function is stupid. So this is my classic example. The limit as x goes to 0, or even better, the limit as x goes to 1 of sine that function. I can't just bring the limit inside. Okay, good. For a start, there's two x's there, which makes it the writing strange. But even if I did sine of the limit over the limit, the problem is that the limit is 0, and sine 0 over 0 doesn't actually exist. Only the limit of sine 0 over 0 exists. So we actually have to do it by substitution. I would say, let u be equal to x squared minus 1. Then, as x goes to 1, u will have to go to 0. Because you know 1 squared minus 1 is 0. And so therefore, by limit law for substitution, the limit x goes to 1 of sine x squared minus 1 over x squared minus 1 will be the limit. Now, the x goes to 1 is replaced by u goes to 0. The x squared plus 1 is replaced with a u. I get that. And the limit of sine u over u as u goes to 0 is 1. Because they might as well be x's, right? That's using the limit law for substitution. Why does that matter? Well, they keep giving you questions where you need it. I mean, You are allowed to skip the whole law if you're paying attention. So just as another example, that, even better, let's just make it. So this example has a whole lot of stuff in it but it also uses this rule that I'm just using. So the top and the bottom are both 0. I could use L'Hopital's rule, but it's not going to help because I'm still going to have, well, it might actually, L'Hopital's rule would be great. But if you were told not to use L'Hopital's rule, what would you do? Okay, that's the key. So, because if I did that, I get like 2 cos 2x and 2 cos and 3 cos 3x, and cos x is 1 when x is 0, so yay! But if I was not allowed to use L'Hopital's rule, what would we do? Well, okay, so we've got a 0 over 0. I'm not allowed to use L'Hopital's rule. Can't factorise because they're not polynomials, so I should search for the fundamental trig limit. I'm going to do that. Technically there's a 1 just here and here. If I'm really clever, I'll put an x in both of those spots. Now my fundamental trig limit tells me what sine x over x is when x is 0. But because of the limit law for substitution, as long as the things that are here inside the sign on the bottom are the same as each other, and as long as they both go to 0, I can use the fundamental trig limit. So if I put a 2 here, and I can't just go putting a 2 there without putting 1 on the top as well, then these will match. And the limit law for substitution says if I call this u, I'll have sine u over u, it'll be great. And if I call this 3 and put a 3 there to cancel it out, then the fundamental trig limit upside down does this one for me. And so I can say it's 2/3 times 1 times 1, which is 2/3. Lovely. So there were some Maple TA questions where they said, write this as sine something over something and cos something over something with an f of x. So that's what they're getting at, that sort of thing. All right. So I technically at this stage use my limit law for substitution because I've called u equals 2x, and in this one I've called u equals 3x. Right. Have I covered almost all limit sort of situations? They're raw limits, pretty much. Anyone, before I move on, does anyone have any other questions, exam questions, tute questions that were limit oriented that you wanted to ask at this time?
What if it's absolute x, absolute value?
What if it's an absolute value of x? Okay, that reminds me, I've missed a limit law. It's even better than a law. It's not just a law, it's a theorem. I'm just going to check though. Yep. The Squeeze Theorem. This is my absolute last resort when dealing with limits. Okay? And it deals with absolute values quite well. I should point out just the limit of absolute value of x as x goes to 0 is 0. Okay, so you can just it's a perfectly good function, it's a continuous function, you can just sub it in. Okay? So that's just worth pointing out. So the Squeeze Theorem is designed for situations in which it's just crap. Okay? The sine x over x is proved using the Squeeze Theorem. Okay? The whole point of the Squeeze Theorem is to come up with two other functions that your function is between. So it goes like this. If f of x like that, for x close to some point A, whereby close to we mean, well, as close as you need it to be, but not technically equal to A, you don't care what happens there. If the limit as x goes to A of f of x is L, and the limit as x goes to A of g of x is also L, then, sorry, h of x, you've got to do the two outside ones. Then the limit as x goes to A of f of x, g, is also L. Okay, so basically it says if the two outside ones go to the same limit, then the middle one has to as well, because it's squeezed between them. Hence the name squeeze. Okay, so what we're doing is we're figuring out our limit by giving up and figuring out some other limits instead. Okay, that's how the squeeze theorem works. And the classic examples of squeeze theorems involve absolute values and sines and causes. So I'm just going to do a couple of examples. This is a classic. The limit as x goes to 0 of x of sine 1 over x. Okay, that's really hard. Okay, can't chuck this in here because the 1 over x the limit doesn't exist. Stuffed. I should point out Squeeze law works at infinity as well. Okay, so usually they'll warn you that you're supposed to use the squeeze law, but it's usually a clue that there is a trig thing. Trig things are really amenable to squeeze law, and also that horrifying, nothing else works, right? You've tried everything else in your head and going, no. Okay, I could if I wanted. This would be really cool. I could try and go, this is the same as sine 1 over x over 1 over x, which is a fundamental trig limit, but 1 over x totally doesn't go to 0 when x goes to 0. So, damn. Okay, damn. So, we're just going to have to do something else. What we're going to do is we're going to try and put this between two other things. To use the squeeze theorem, I need to have this, and it needs to be greater than or equal to and less than or equal to something. Okay? All right. Sine. And I usually start like this. Pick out the bit that's got a trig thing. Sine 1 over x, regardless of what 1 over x is, sine is always between plus and minus 1. That is always true. Sine of anything is between plus and minus 1, regardless of what the thing is. Okay? And then I multiply, and then I try and take this equation and do something to it to produce this, or inequality, you like. There's a technical issue here, so I'm just going to have to deal with it separately. So if I multiply everything by x, I'm going to have two columns here, by the way, and leave a little bit of gap. I'm going to write something there too. If I multiply this by x, I'll get minus x is less than or equal to sine of 1 over x, which is less than or equal to x. Sorry, x sine 1 over x. Okay? Which is great. X sine 1 over x is the function I want, I'm looking for. It's between both of these, and both of those goes to 0 when x goes to 0. So this is how you go to like the limit as x goes to 0 of minus x is 0. The limit as x goes to 0 of x is 0. Therefore, the limit as x goes to 0 of the middle function is also 0 by the squeeze theorem. And just writing the word squeeze is fine. Okay, and when you use the squeeze theorem, you must have those three parts. Okay, 4 parts. You have to have the statement that it's between, which is this statement here. You need to say the left-hand one is whatever it is The right-hand one is whatever it is, therefore the middle one is whatever it is. That's how the squeeze theorem is applied. There is a technical issue here, though. It's worth mentioning. If x was negative, when you multiply by a negative, all your inequality signs flip. So, damn. So this only works if x is positive. X is positive. If x is negative, if I multiply everything by x, I'll get minus x is greater than or equal to x sine 1 over x, which is greater than or equal to x. Because when you multiply by a negative, your inequality signs flip over. But if that's the same, it's the same. It's just that the minus x is on the other side to the x. So the limit as x goes to 0 of minus x of x is 0. You know, and in fact, if I was really clever, my working could look like that. So regardless of whether x is positive or negative, x sine 1 over x is between minus x and plus x, and because they both go to 0, the function does anyway. So you could write your working like that, or if that makes you uncomfortable, you could do the two separate parts separately. So perhaps, probably a good idea might be at this stage just here to say no. So in either case, this function I want is between minus x and x. It's just between in the opposite direction. Okay. What if there was an absolute value? I'm going to do the same example. But with an absolute value on the x. This one's easier. So my sine 1 over x is still between 1 and minus 1. It's always between 1 and minus 1. And I multiply everything by mod x. And mod x is positive, so I don't have to worry about flipping inequality signs, because mod x is always positive. And then I can say, well, the limit as x goes to 0 of minus mod x is 0, because minus mod x is a perfectly good continuous function. And the limit as x goes to 0 of mod x is 0, because mod x is a perfectly good continuous function. I can just sub it in. And so therefore, the limit as x goes to 0 of mod x sine 1 over x is 0 by the squeeze theorem. So this one's actually easier. The one where it was just x, I had to deal with what happens to the inequality signs when I multiply by x. But this one, nah, easier, because mod x is positive anyway. And I should probably do one more. What if the whole thing was absolute valued? Well, there are two approaches to this. One is to try and put the thing that's between them, between two numbers. And the other one is to try and put the thing that to separate the mod, because mod can be expanded out over multiplication. I'm going to do the first one. No, the second one. So that's the same as the limit as x goes to 0 of mod can be expanded out over multiplication. And then I'm going to look at the part that involves trig. So I've got that sine of 1 over x is between minus 1 and 1. It's always how it's going to start, because that's what's going to give me my squeezy functions. And then I need to absolute value it. Okay? So if you absolute value something that's between plus and minus 1, the answer will have its size is still 1 at most, but it can't be negative anymore. So when I do the absolute value, I'll get this. Okay? So the ones that were negative, the part that's minus 1 is minus 1 is less than or equal to sine 1 over x is less than 0. When I modded that, it became from 0 to 1, and the part that was already positive stayed positive, so that's what happens. So I would say that if these two numbers were different, if this was a 2 and this is a 1, not that it will happen, but if this was a 2 and this was a 1, you would take the absolute, it would always be 0 here, and this would be whatever the biggest of those two numbers was. All the same, now I can just multiply everything by mod x. And I can use the squeeze theorem. The limit as x goes to 0 of 0 is 0, and the limit as x goes to 0 of mod x is 0, and so therefore the limit as x goes to 0 of mod x sine 1 over x is 0 by the squeeze theorem. So they're all roughly the same, there's just a little quirk somewhere in the middle that you have to deal with. So I'd imagine that would be worth possibly 2, possibly 3 marks, but only one of them is for that quirky bit.
When you've got a limit that includes, say, absolute value of x minus 2, and it comes to two different values at that point, should you say the limit from above doesn't equal the limit from below, therefore it doesn't exist, or do you just say there's a discontinuity at A?
Okay, so you're saying an example something like this. Something like that?
Yeah.
Good example. Okay.
So what is the graph of that?
Oh, I know what the graph of that looks like. The graph of that looks like, I believe the graph of that looks like this.
Oh, yeah. That was obvious.
Well, after, I thought for about a minute there, so it's not that obvious. Okay, and I'm very experienced in this area, so, obvious to me.
Yeah,
Okay, so the key is, if there's a raw limit with an absolute value in it that doesn't have a trig function in it, then the squeeze is probably not going to happen. What you want to do, a really good thing to do is to say, what would happen if x was really close to the number on both sides? So when I went back in these ones, these ones had trig stuff in them, so they felt squeezy. But when I look at this, and I go, if x is really close to 0 but positive, I'll get sine of something times really small number, so it should come out to 0. If x is really close to 0 but negative, I'll get really tiny negative number times something, so it's still going to be close to 0 but on the other side. So the feeling is that it should go to 0. But if I look at this, if x is really close to 2 but above 2, that number there is positive, and so is that number, and so I'm going to get a positive answer. If x is really close to 2 but less than 2, then x minus 2 will be negative, but mod x minus 2 will still be positive, and so I'm going to get a negative answer. Okay? So if I come in from one side, I'm going to get a negative answer. If I come in from the other side, I'm going to get a positive answer. And a negative can't be equal to a positive. So it's likely that that limit isn't going to exist because it's going to go to two places differently. So we're going to go... So this is your final thing that I didn't mention anywhere so far. The final thing is, there is one situation you need to be careful of, is that when the limit is different from two different sides. And the best time to tell is when there's an absolute value involved. So thank you very much for mentioning it. So I'm going to have to do the limit from above and below separately. The limit as x goes to 2 from above, as in from the right. Okay. When x is above 2, x minus 2 is a positive number, which means that mod of x minus 2 is still positive. It's the same as what it was before. So I get this. Okay, so the mod has become the plus version of the mod. So the x minus 2 and x minus 2 cancel and I get a 1. But if I go from below, if I'm on the left-hand side of 2, then x minus 2 is negative. So if I had 1.999, I get negative 0.001. And when you do the mod of a negative number, you have to add an extra minus to make it positive. One way I have of thinking of this is that mod x minus 2 is plus or minus 2. Okay, all by itself, regardless of whether you're... And so in my head, this is what I thought. I thought mod x minus 2 is plus or minus x minus 2. Okay? Sorry, that's... So the mod all by itself, regardless of whether it's an equation or not, is plus or minus. The fact that there's two options for what it could be is telling you that you need to split your limit. And when is it plus and when is it minus? Well, it will be the plus if x is above 2, and it will be the minus if x is less than 2, is below 2. So that's why I replace the mod x minus 2 with minus x minus 2. And then when I cancel them, I get 1 over minus 1, which is minus 1. So the two limits don't match, so therefore the big limit doesn't exist. So the limits are not equal, so therefore the limit as x approaches 2 of x minus 2 over mod x minus 2 does not exist.
So is that the expected approach you should take rather than just saying there's a discontinuity at that point?
So I've asked, is this the expected approach rather than saying there's a discontinuity? Yes, because the only way to rigorously tell the reader that there is a discontinuity is to find the limits anyway.
So the definition of the discontinuity is that the limit doesn't.
Yeah. So the definition of a discontinuity is that the limit doesn't exist. So to convince the reader that there really is a discontinuity, you'll have to find the limit anyway. So you might as well just find the limit. Okay, that's probably enough, unless someone has another question that's a limit oriented.
It is, but it's algebra limits.
Okay.
Multivariable calculus limits.
Ah, multivariable limits. There, let's do that. See, the thing is, when you study, you do things in a different order than they are in the course. So let's do that now. Of course, they'll only ever give you two variable limits, which is nice of them. Okay, so all your limit laws still apply. Okay? So, I should probably put the definition, shouldn't I? Okay, so the limit as xy goes to some point a, b of f of xy. That's what we're looking at, that sort of thing. Good thing that my friend over there gave me his calculus notes, his algebra notes too. Now, there is a proper definition of this if you ever do, multivariable calculus as a course. But it goes something along the lines of that limit equals L, say, if no matter how close you want to be to L, there is a closeness, there is a very small distance around the point AB that will guarantee that you're that close. So the closer you are to AB, the closer you are to L. That's basically what it means. So not you are, but the closer xy is to AB, the closer f of xy is to L. With a key point that this must be true no matter which direction you get close to AB from. So regardless of the direction or path of approach even, doesn't matter how the path goes. If it's a curved path, it has to work too. So regardless of the path or direction of approach, okay? That's when the limit exists. Yep?
So in the scope of this course, we expect to be able to just prove there's not a limit, being able to prove there is a limit.
Yeah, so I've got so the question from the floor is, in this course, in the scope of this course, are you ever asked to prove that there is a limit or only to prove that there isn't? Mostly isn't, but there are a few specific situations in which you can show that there is a limit in this course. Okay? And I will show them both. Okay. So it goes like this. So if you choose, So what are we going to how are we going to approach it when we're faced with a limit? So what to do if you are faced with a multivariable limit and you want to know what to do? So the first rule is that division law from ordinary limits applies. Okay? Okay, so if you do like, as an example, that the limit at the top is not 0, the limit at the bottom is, therefore the limit doesn't exist. X minus 1. Therefore, original limit does not exist. Okay? If, however, the bottom isn't 0, just sub it in, right? That function there, well, it's just, 0 squared plus 1 squared over 0 minus 1, which is minus 1. Okay? So that's the simplest one. So if it's a division and when you sub it in, there's no problems, just sub it in. If the top isn't 0 and the bottom is, it just doesn't exist. So that's okay. All right? That's good. Number 2 is try various paths. This will only prove that something doesn't exist, though. Okay, so
prove that it does exist, you have to show that it does exist for any possible path, but in order to show it doesn't, you just have to find one where it doesn't.
Yeah. So you're right. So in order to show that it does exist, you have to show that the limit exists and is the same answer for all possible paths, right? Including spirals and parabolas and all sorts of crazy crap, which is actually impossible, right? But if you want to show it doesn't exist, you either just have to find one path where it doesn't exist, or two paths where they do exist but come to different answers. And the paths you should choose usually are x equals something, y equals something, and x equals y. That's your best bet. But you want to choose something that will allow you, and it's always a fraction that's in the issue. It's always fractions that are the issue. You want to choose something that causes something to cancel so that you can see what's going on. Okay? That's your goal. So choose something to sub in that will make stuff cancel. Okay? Actually, you know what? This is wrong. Ignore what I said earlier. What I just said before is wrong because that limit also doesn't exist. Sorry. Okay? So I should go back. Your limit law for division also only shows that things don't exist. So just the something over 0 division law. That's the only one that works, okay? Sorry about that. I'm glad I fixed that because you would all have done something wrong in the exam and then come and said, David, you told me that you could do that. So I shall try some different paths. So the first ones to try, just do them in your head before you commit to any of them. So I'm going to the point 0, 1. So I could choose to make sure that the line I approach on is just where x is 0. So if x is 0, I'll get y squared over minus y, which will give me minus 1 when y is 1. If y is 0, I will get x squared over x, which will give me 1. Yay, doesn't work. So the limit, so approach where x is 0, the limit as y goes to 1 of 0 squared plus y squared over 0 minus y is the limit as y goes to 1 of y, which y squared of minus y, which is minus 1. The limit as x goes to, so choose the line y equals 1. The limit as x goes to 0. Oh, okay. Crap, I wasn't 0, but that's okay. That limit is also minus 1. Damn cursors. I shouldn't have committed myself so soon. I've committed the cardinal error. Of subbing in 1 and thinking it's 0. Happens all the time. Because I cross the y's out, but they're actually 1s. Okay, maybe this limit does exist. I think it doesn't though, pretty sure. So, what if I chose x equals y? Now it's going to be stuffed, right? Because that's never true if x is equal to y. So if I choose x equals y, the bottom's going to be 0 for all possible x's and y's. And so my function doesn't exist at all if x is equal to y, so that's bad. Okay, so what if y is 2x? Alright, and the reason I'm going to do that, because then I'm going to get like x minus 2x, so I'm still going to get an x. Let's try that. Oh, it has to be plus 1. I've chosen a bad function.
If it doesn't exist at all at y equals x, doesn't the limit not exist?
Yeah, that's true. But y doesn't equal x. Well, mind blown. I can't choose y equals x because at the point 0, 1, y doesn't equal x.
Ah.
Okay, y equals mx.
Sorry?
You get y equals mx.
I can't go y equals mx because at the point 0, 1, y is not mx. Because if it was mx, it would be m times 0, which would be 0. I should choose something like y equals x plus 1. Because that line does pass through 0, 1. Let's give that a go. Okay, I've subbed in y equals x plus 1. You've now seen the danger of choosing examples off the top of your head. So x minus x plus 1 is just minus 1. Oh, maybe the limit does exist. Damn. I give up, really. If this happened to you in an exam, you would say, the limit probably exists, I give up. This is not worth the 1 mark that you gave it to me. So that limit actually is perfectly good because it's just a constant on the bottom. So that'll be 0 squared plus 0 plus 1 squared over minus 1, which is minus 1, sadly.
Isn't that why all the questions are in blocks, like A, B, C, D, E, 8 marks from all of the above?
Yeah.
It doesn't give the game away if you can calculate this limit or say it doesn't exist out of 1.
Yep. So I will say something. Almost always in an exam, the limit is at 0, 0. Which makes it easier. I have a feeling if I did like y equals x squared plus 1, that's when there would be something horrifying happening, but I'm not going to do it. So I'm so sorry. I'm actually going to give up on this one.
If the limit did go through,
Sorry.
It wasn't 0, 0, and you used y equals mx. Would that result if it was, say, 2 half m? Would that be enough to prove that from two different values of m?
Yeah, so I've been asked, what if it was going through 0, 0, where y equals mx works, because 0, 0 is on y equals mx, and if when you did the limit, all the x's and y's cancelled and you end up with just something involving m, yes, that would show that the limit doesn't exist. But personally, I get really confused when I do that, so I like to just pick values of m, because that'll work just as well. Yep,
If the limit was
just a second.
If you're saying that we have to show that it exists for any function like does that mean you have to try does that mean you have to try f of x itself?
So you're saying we have to try f of x itself. Well, they won't give you one that's required for. So yes, because I'm almost there. I do have one more trick up my sleeve. So I'll give up and get back to this later. Okay. Okay. I'm not going to give up completely, but with this, if I'll do one that does go to 0. And do that one. I can do that one. Okay, so this one will... I need it to not exist, don't I? Give me a second. I might change the question, so give me a second. Oh, yeah. Almost there. Yeah, okay, this will work. I hope. Actually, can I do it the other way around? Okay. I feel better about this one. Okay, so this function, the only place it doesn't exist is 0, 0. Okay, because the bottom is always positive unless they're both 0. So I don't have to worry about that horrifying discontinuity in the other one. So in that first one with the x minus y, that one just won't exist anyway. Because the only place this doesn't exist is at 0, 0, so that's great. And if I sub in x equals 0, let's just check this, I'll get y over y squared, which is 1 over y, which doesn't exist. Damn, I'm really trying hard here. But I'll do that one too. So x equals 0, I get the limit as x approaches as y approaches 0 as well, of y over y squared, which is the limit as y approaches 0 of 1 over y, which does not exist. So therefore the original limit doesn't exist. That's an important case. If one of the limits, any of the limits doesn't exist, you can stop. And now I'm going to actually search for a pre-existing example. I've got one.
Last paper.
Yep.
Is x squared plus y squared over y minus 0, 0.
Still feel uncomfortable about that one because it's this horrifying discontinuities along xy, but it's okay, you only have to approach it inside its domain, so I think it'll be fine. So, well, that one smacks of a different form to me, but if I can't choose x equals 0 or y equals 0, because it's not defined when x is 0 and when y is 0 at all, ever. Okay? So if x is 0 but y isn't, it's not defined. So I can't choose that. So I can't do x equals 0 as undefined for all y. I can't do y equals 0 as undefined for all x. Okay, so I'm going to have to choose something else. So I could choose y equals x. So I've got so I've replaced my y with x's. I've gotten to this, the x squareds cancel, and I get the limit as x goes to 0 of 2, which is in fact 2. Okay? So what a lot of people would have done is go y equals mx. I just can't be bothered. Like, I'll just go, alright, well, what if I chose y equals something else x? 2x is fun. And the reason I would do that is because I know that if y does equal x, the bottom will sort of be x squared-y, and the top will be x squared-y, and so they should cancel each other out. So I'll get the limit as x approaches 0. So I've got x squared and 4x squared, so 5x squared on the top. On the bottom is 2x squared. They cancel. My limit is 5 over 2, which is not the same as the other one. I can stop. So the mx thing's a great plan, but I just don't think of it. I just try different numbers until I get one that's different. So the original limit does not exist. Okay, so the final strategy to use, which you may use before this if you want to, is to use polar form. Strategy 3. Use polar form. Now this will allow you to show that a limit exists, by the way. The other ones will only allow you to show that a limit doesn't exist or increase the evidence that it should. I should point out that if I had x squared and x to the 4, I would have gone y equals x squared so that everything was in, like x to the 4 and y squared, I would have gone y equals x squared so that everything was x to the 4 so that stuff could cancel out. But using polar form will allow you to show that a limit exists. It will also allow you to show that a limit doesn't exist. And it's specifically to things where you happen to notice, and it will usually happen in things where there's an x squared plus y squared. Okay, that's when you really want it to be. Okay, really good for things that have an x squared plus y squared in them. So let me try that other limit that I was doing and go to polar form instead. Yes. Not x approaches y, xy approaches 0. Oh, that's not going to work either. I can't do that other limit. I just give up. Okay. It also only works for xy approaching 0, 0, by the way. Okay? So this final approach is really good for things that have x squared plus y squareds in them, and it only works if xy is going to 0, 0. Which is why most exam limits go to 0, 0. I'm just going to look. Surely this is in the notes. Maybe it's not. Oh yeah, there it is. Yep, thank you. Let's do the other one, but upside down, hey? So what we're going to do is we're going to sub in x is r cos theta, y is r sine theta, and x squared plus y squared is r squared. Okay, that's what you sub in. And then your limit as xy goes to 0, 0 will be the limit as r goes to 0. Xy goes to 0, 0 is replaced with r goes to 0. That's what you sub in. So you have the limit as xy goes to 0, 0 of xy over x squared plus y squared is the limit as xy goes to 0, 0 of x is r cos theta, y is r sine theta, x squared plus y squared is r squared. Alright, this is r goes to 0. Sorry, forgot to sub that in. And so I get the limit as r goes to 0, the r squared cancels with the r's of cos theta sine theta, which doesn't involve r. So it's going to be different for different thetas. So the limit does not exist.
So if it doesn't go down into an expression purely involving r, then
Yep. If there's any thetas left after you've done the limit, it doesn't exist. Unless there's a magical trig identity that turns it all into a number, right? Okay? If I'd done that the other way around, it still wouldn't have existed. And I'm going to show you. But if I change this question ever so slightly, and change it to that, and do my subbing in, you don't have to write all that down necessarily, but it's only actually necessary to write that bit down, but I like to write them all down just to remind myself what's going on. Then my limit okay, so when my xy goes to 0, 0 becomes r goes to 0. The x squared becomes r squared cos theta squared. The y becomes r sine theta. The r squared on the bottom, the x squared plus y squared becomes r squared. That cancels with that, and I still have an r. Which is great, because as r goes to 0, anything times r goes to 0. Not r, sorry, wrong way around. With respect to r, this counts as a constant, and so I can bring it out. Because that limit there is 0. So I have cos theta squared sine theta times 0, which is 0. This shows that the limit exists and is 0. And it's the only one you know that will show it exists, unless you just sub it in and there's no problems with subbing it in. So you'll find that if there will be an x squared plus y squared in it somewhere, or when you do polar form, if the limit exists, there will be more r's on the top than there are on the bottom. Because then they'll cancel each other out and stuff. Right, so let's just summarize that. Let's go back and just see where I went. Use your anything over 0 division law. Just doesn't exist. No point doing any special polar or anything for that. If the top isn't 0 and the bottom is, it just doesn't exist. Try various paths. Okay, and in particular you want to choose something to sub in to make stuff cancel. So if you've got a y to the 4 and an x squared, then choose your x to be y squared. But don't spend too long and move on to a different question if it turns to crap. And if it's got an x squared, y squared plus y squared in it, it's a great idea to try polar form, but only if it's going to 0, 0. If your limit doesn't go to 0, 0, then that means that one of the first two ones will work and it won't exist, like in an exam. You know, in mathematics, a life of a mathematician. Well, in the life of a mathematician, you might have to work for several months to figure out what the limit is. So we're not going to put you in that situation. All right. I think that's probably everything I could possibly say about limits. I will, for anyone who's interested in sticking around, keep talking for a bit and answer some questions if you still want to be here.